Hi, I'm Dr. Vivian Lowe. Welcome to VLMD Rounds, a podcast on medical science and tools to optimize your health. So I just realized that I am past the 20th episode mark. I somehow didn't register this until this week. And this is episode 21. So I've made 20 episodes already. And it seems like I just started. So time really flies. Anyway, thinking back when I started, I had a plan, I had a list, and I had a structure for how I was going to approach this. And to be fair, I think it kind of worked for the first maybe 8 weeks. All was well, somewhat. And then, life got in the way. And my structure kind of vanished. And I've just been going with the flow since then. And basically, this is what happens. I kind of do things a little bit on the fly, not exactly, because I put out a monthly newsletter, and those of you who are interested, you can subscribe to that on my website, vivianlohmd.com, VYVYANELOHMD.com. So that newsletter keeps me honest because I basically kind of give my upcoming topics for the month in the newsletter. And so I do plan a little bit, but this is how I plan. And generally, I realize, oops, I got to put out another newsletter. Boy, that month sure flew by quickly, right? And then while I'm at lunch or dinner, just taking a break, I'm sitting there thinking, well, what am I going to talk about for the next 4 weeks, right? And then the first 4 things that pop into my head, that gets on the list. Now, obviously, this is somewhat informed by, requests that people have made and conversations that I've had with patients, maybe things that I've read recently or just had some kind of discussion with someone about. And then somehow it pops into my head and I just scribble it down and hope for the best, right? And of course, that list is tentative. I do once in a while move things around a little bit, but in general, I think I've been pretty good about following, whatever was listed and making those episodes. So somehow today's topic popped out for the month, okay? When I was making up the list for this month. And to be really honest, I'm not even sure why it popped up. I'd always known I would talk about mTOR. I knew I wanted to talk about mTOR, but I felt it would be somewhere further down because it's such a big topic and and somehow it popped up. But when it popped up, the title also came to me at the same time, and that was what cinched it because I probably would have delayed doing this episode, but then I was so tickled pink by the title because I do love wordplay. So I have to admit, I thought, oh, I just want to be able to use that title as soon as possible, and that's why I ended up doing this episode. And also maybe I was a little bolstered by the previous episode. I'd done the one on the glycocalyx for episode 20. And I will say, when I was done, I went, oh my God, there's so many things I left out that I really wanted to stay. And then I realized, hey, I can always do part 2 and 3 and 4 and 5 and 6, right? And so once I realized that, I just relaxed a little bit. And I thought, well, I'll give mTOR a stab right now. And whatever I miss, I can go back, do part 2, 3, 4, 5, whatever, however many that we need, okay? And again, it's really hard, as I said in the previous episode, to decide on what to talk about next, because all these things are connected anyway. And when you're explaining one, another topic creeps in there, and they're all linked, as you'll start to see, like my famous Balzacian world that I've talked about in previous episodes, right? So, with that in mind, I'm just going to plunge into today's episode. There's lots that I am skipping and leaving out, and maybe someday we'll come back and do those if you're interested, if you want to, right? Or maybe we'll move on to other things. But I do think mTOR is a big topic. So let's go. Now, to start off with, everybody starts off with rapamycin, because TOR, all in caps, TOR, stands for target of rapamycin. So what the heck is rapamycin? And it basically was an antifungal that was discovered on the island of Rapa Nui, which is why it's called rapamycin, RAPAMYCIN. Okay, and people thought this would be very useful as an antifungal. However, it had some side effects that sort of scared people off, because rapamycin turned out to be immunosuppressive, and it was also anti-proliferative. And so in the end, they kind of dropped the usage of rapamycin as an antifungal. And since then, we've discovered other things about rapamycin that have made it intriguing. But what rapamycin acts on is actually this enzyme that is named the target of rapamycin, or TOR, T-O-R. Now, TOR is conserved really evolutionarily across all species. It's a very, very important protein. And so you see it in all species. You see it in yeast, you see it in flies and in worms and in humans, of course. So initially, we used to designate, what kind of TOR it was by, putting the little sort of prefix before it, the M, okay? And the M stood for mammalian, okay? To distinguish it from yeast or fruit fly or insect TOR, okay? Because while we have this protein, it's different. It's associated with different subunits and acts differently. The pathways are different in different species. So to make sure we know that we're talking about mammalian TOR, we called it mTOR. And then somewhere along the line, it's a small m, the TOR part, T-O-R, is in caps, and then the M is small. Somewhere along the line, it was switched to mechanistic target of rapamycin. So that's what people now refer to it as. And I just feel like, well, that wasn't very useful, because when you say mechanistic target of rapamycin, it could be in frogs or Drosophila or earthworms or yeast or human. So which one are we talking about? So I think it would have been better just to keep the mammalian, and some people prefer to use it. And I prefer to use mammalian because at least it gives you some additional information. Mechanistic doesn't really give you any additional information. All right, so I ranted on enough about that. It's called mTOR. Now, in mammals, right? All right, so TOR is, as I said, an enzyme, and it has two units, okay, that make up the full TOR. So it's a dimeric protein with two sort of similar, actually same units, joined together. And it's part of what we call the PIK family of enzymes, PIKK family of enzymes. So TOR can be itself can be associated with other proteins, other subunits, right? And it turns out in mammalian TOR, we have different subunits that are associated with the TOR part. And therefore, we actually have two complexes, right? We have mammalian target of rapamycin complex 1 or mTORC1, and we have mTORC2. And the reason we have those two different complexes is because there are different protein subunits that are attached, right, to the TOR part. Okay, so in mTORC1, the main protein subunit that is attached to it, we know as RAPTOR, RAPTOR. In mTORC2, we have RICTOR attached to it, okay, RICTOR. And that's what distinguishes the two complexes. It turns out also that we probably have a third complex called mTORC3. And this is when TOR is associated with a transcription factor called ET7. And this ETV7, when associated with the TOR, becomes mTORC3. And we see this highly expressed in cancer cells. Now, this is probably what makes the cancer cells insensitive to rapamycin. Because remember, rapamycin acts on TOR, which is the target of rapamycin. And I didn't tell you this, but when it acts on TOR, it inhibits the action of TOR, okay? It inhibits the enzymatic action of TOR. So when you have cancer cells, they often highly upregulate mTORC3. mTORC3 has characteristics of both mTORC1 and 2. It has some of the things that complex 1 has and some of the things that complex 2 has, but it's also missing things that complex 1 and 2 have. So it's this mishmash of different characteristics. And, you know, we do know it's insensitive to rapamycin. Actually, if you get rid of the ETV7 part of the TORC unit in mTORC3, that's when the cancer cells become sensitive to rapamycin again. So we know it's that transcription factor that's probably making them insensitive to rapamycin. Now, in terms of TORC1 and TORC2, TORC1, which is the more famous complex, is sensitive to rapamycin. So rapamycin is able to bind to it and inhibit its action. And TORC2 does not have rapamycin sensitivity in the acute situation. But in the long term, over time, it too is sensitive to rapamycin. Okay. The reason for this is because of those different subunits that are attached to the TOR complex, right? So remember, RAPTOR is attached to TOR in mTORC1. There's also another subunit called FKBP12, right? That's attached to TOR in mTORC1. And that little bit, that little protein is what rapamycin is able to bind to in mTORC1. And when it binds, then it covers the catalytic site, right? It's just kind of bulky and, you know, because of steric hindrance, doesn't allow, you know, the enzyme to operate, okay? So that's how it inhibits mTORC1. Now with mTORC2, remember mTORC2 is bound to RICTOR. And RICTOR actually is attached in such a way that it kind of hides the FKBP12 part. And because of that, then rapamycin cannot bind to mTORC2. And so mTORC2 is acutely not sensitive to rapamycin. However, over time, it becomes sensitive simply because when the actual complex is being formed, the TOR part initially isn't yet bound to Richter. And at that point in time, FKBP12 is exposed and can bind to rapamycin, right? And when that happens, then Richter can't even bind. So essentially, over the long term, you can't even make mTOR2. And so that's how it somewhat becomes sensitive to rapamycin, because you can't make it anyway, right? All right, those were just some details about the structure. Now, when you talk about mTOR, I think most people maybe have heard of it from the bodybuilding world. Certainly, there's a lot of talk in the bodybuilding world about mTOR because everybody's interested in building muscle. And what is the function of mTOR? Well, mTOR is famously known for protein synthesis, right? And so in the bodybuilding world, that's translated into building muscle, making more muscle, because muscle, after all, is made up of proteins, right? So that's where, a lot of people are familiar with mTOR. And that's not a bad place to start. In fact, we'll start there ourselves. But I just want to have us look at other aspects of mTOR as well. So if we go to the bodybuilding world, then classically you want to make some protein, you want to make more muscle. So you go to the gym, you work out, but then you also want to be consuming proteins, right? You need some building blocks. So you need those amino acids that are the building blocks of proteins. And you want to supply that to the muscle cell, okay? And famously, again, in the bodybuilding world, everybody talks about the amino acid leucine, which is a branch chain amino acid. You take leucine, right? You take about, 3 grams of leucine and you're all set, because you're going to turn on mTOR. That's what you'll hear. And what does it mean when you turn on mTOR? Well, because mTOR works on protein synthesis, then you're going to build muscle. All right, so classically, you take leucine. You got to take enough, though, because kind of like a switch. You take enough leucine and you'll turn on mTOR and you make muscle. So, everybody ends up taking leucine in their supplements, because obviously we all want to make muscle. All right. Let's actually step back a little bit and see what this whole system is about, okay? Because we have mTOR, yes, it's a machinery for making proteins, right? It upregulates ribosomal proteins and then also, the translation of proteins and so forth. So you can think of it as this factory to start off manufacturing proteins. But first of all, it has to know when to work, right? When should I start making protein, right? When do I start helping the cell to grow? Well, it has to then detect the availability of nutrients. Okay, so obviously when you have enough nutrients, you have the building blocks to make protein, you have enough amino acids, then you're good. You can start, working on making more protein. So you have to be able to sense that you have the nutrients available. And once you can sense that, then you can make more protein. In addition, you don't want to work against yourself, right? You're busy making protein. So the last thing you want to do is have the cell also be breaking down protein. It's just undoing my work, okay? So mTOR is able to inhibit something called autophagy, right? To break down protein. So autophagy basically means self-eating, and it's a way for the cell to recycle its bits and organelles that are damaged. And it does so by just basically digesting those damaged bits, right? And then we'll use the parts to build something else. Okay, it's kind of like this recycling plant. you go there and you disassemble, whatever damaged bits were there. And then now you can build something new using those parts. I remember when I was a med student, I used to go to the junkyard to try and get used car parts whenever I needed something fixed in my car, because it was very expensive to get new car parts. And you just go to the junkyard, and basically people would junk their cars and they would strip the cars of anything that might still be useful, right? And then they'd resell it. And then, if you were a med student on a budget, that's where you went to replace your car parts, right? It's kind of what autophagy is about. So it's this junkyard and you recycle those parts. Well, okay, we don't want to be breaking down protein, right? So mTOR actually inhibits autophagy, and also it inhibits the formation of lysosomes. Lysosomes would be where the breakdown of proteins happens, right? And so, yeah, we don't want that. So we'll also inhibit the formation of lysosomes. So essentially, if you step back, mTOR says, I got this job, I gotta grow, I have to help the cell grow, in essence. And basically that's an anabolic process. If you remember, that's building tissue, right? So I need the nutrients for that. And then I also need to make sure that we stop any catabolic processes going on, because that's just going to be working against myself, right? As I'm building, I don't want things to be broken down at the same time. So that's the overall function of mTOR. Now, I am going to briefly go over the pathway. It's a very complex pathway, and I don't want to go over every single bit, because you can look that up. And, ultimately, I want us to have the big picture view of mTOR, all right? But there are some parts that I think it's important for us to talk about and to understand, all right? So, right, we said that we need to basically detect nutrients. And if we go with the bodybuilding, version of this, right? Leucine, Leucine, that amino acid is really important. So obviously we have to be able to know when we have leucine in the cell. So we've got to have a leucine detector. And this detector turns out to be something called sestrin 2, S-E-S-T-R-I-N, sestrin 2. So that's the leucine sensor, okay? And when sestrin 2 detects leucine in the cell, then it's going to act on something called GATOR2, G-A-T-O-R2, don't worry about it. But it acts on GATOR2, right, to do something, okay? And what it's going to do is it's going to start to activate mTOR via GATOR2. Now I'm going to take you to another part of this complex, and there is a scaffolding protein that's called the ragulator, R-A-G-U-L-A-T-O-R. Okay, again, that's a play on TOR. You'll see all these names have T-O-R at the end, right? Lots of wordplay with mTOR. Maybe that's why I like it so much. All right, so the ragulator is a scaffolding protein, and it's tethered to the lysosome. Now, attached to it too are these subunits, and they are called Rag ATPases. And we don't have to worry too much about them. We have Rag A or B ATPase, and we also have Rag C or D ATPase attached to the ragulator, which is this big scaffolding protein that's tethered to the lysosomal membrane. Now, you can think of, first of all, Rag A/B. The reason I call it that is because the A form and the B form are really, really very similar. They're pretty much the same, right? So it could be A or B. Either one will work, okay? We have both of them, and either one will work. So pick one, A or B, right? And the same with C or D. They are both very similar. And so if you use C, it's fine. If you use D, it's fine. They're basically the same, right? So there are 4 possible combinations, right? Because you have to have both of these subunits together. So you can have Rag A with Rag C, or Rag A with Rag D, ATPase. You could have Rag B with Rag C, or Rag B with Rag D. So, those are the possible combinations. But, whatever you do, you have to have Rag A or B with Rag C or D. Okay, and you can just simply think of them as switches. Okay, and once we have cestrin 2 act on GATOR, what GATOR will do is it will actually turn on the mechanism that switch, okay, whereby these Rag ATPases are switched on. And once they are switched on, what do? Well, they actually help bring mTOR from the cytoplasm to the lysosomal membrane. So they actually help translocate mTOR from the cytoplasm to the membrane. Okay? And that's very important because the lysosomal membrane is where all the action is. Okay, so that's one arm of the mTORC1 complex that I'm talking about here. Right, so again, just to do a quick review, we have to sense leucine, and we do so with cestrin 2. Cestrin 2 then acts via GATOR2 to activate mTOR. How does it do that? Well, it acts on the Rag ATPases on the regulator, which is tethered to the lysosomal membrane. And once it does it, it kind of switches them on to bring mTOR to the lysosomal membrane. Okay, so simplistically, we can think of it that way. But there's another part. Okay, and the other part is through the action of growth factors. Okay, so that is a big difference between, let's say, mammalian TOR and yeast TOR, for example, unicellular organisms, right? They really don't have to worry about growth factors because they're just one cell. But if you have multicellular organisms, then you have to coordinate all the cells in terms of growth and proliferation, and we can do so through growth factors and through hormonal stimulation, right? So we have that extra bit in multicellular organisms. So with growth factors, in this case, insulin, right? Insulin is going to work through what we call the PI3K AKT pathway. Don't worry about it, but it's phosphatidylinositol 3 kinase pathway, PI3K, and also the AKT pathway, also known as protein kinase B. Don't worry about it. Why do I say that? Don't worry about the names, but it works through that pathway. And what does that do? Well, let's back up a little bit. There are these protein units called tuberous sclerosis complex 1 and 2, and they're bound together. And I'll just call them TSCs, okay? TSC2 is actually bound to another protein called RHEB, RHEB. And it binds to RHEB and just prevents RHEB from doing its job. So you can think of it as, how you have a lot of work to do and you're very busy, and then one of your friends comes over and they keep distracting you and keeping you from your work. So that's what TSC does to RHEB. Okay, RHEB's got this job that it has to do, but TSC2 is preventing RHEB from doing that job, just distracting it, blah, 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 blah. Okay, so preventing RHEB from doing its job. However, once we activate that PI3K AKT pathway, that is going to act on TSC2. Okay, and what it's going to do is stop TSC2 from, from interfering with RHEB, okay, and interacting with RHEB, And this will free up Reb. Okay, and Reb goes, oh my God, thank God, now I can do my work. And that work is to go to the lysosomal membrane. And there it can directly activate mTOR, right? And cause mTOR to start its process of protein synthesis. Okay, simply put. So you can see there's just two pathways that we have to consider. One is activated by nutrients. In this case, we looked at leucine. And once leucine was sensed, it set up a series of reactions that ultimately brought mTOR to the lysosomal membrane from the cytoplasm. Okay. Now, in the cytoplasm also is Reb, but it's being kept from doing its job by TSC2. But once we have the action of insulin through that AKT pathway, we can act on TSC2 and free up Reb, right? And now Reb can do its job, and Reb will also go to the lysosomal membrane. So see, everybody wants to meet at the lysosomal membrane. And once it's there, it can directly activate mTOR and start the process of protein synthesis. So I know it's a little complicated, but I think it's worth kind of keeping that big overall picture in mind. There's one other thing attached to the regulator, which is tethered to the lysosomal membrane and also attached to the Rag ATPases, right, is another protein. It's part of the solute carrier family. It's called SLC38A9, right? And it's attached to the regulator. It's also sitting in the membrane, okay? So that's important. I just want us to keep that piece in mind as well, because we're going to come back to it. So now you just have this big overall view of, generally how mTORC1 is working. It's first brought, senses the nutrient, and then goes to the lysosomal membrane. And then Reb also goes to the lysosomal membrane once we activate the pathway through growth factors like insulin. And now everybody's at the meeting point, the lysosomal surface, and now we activate mTOR, and mTOR can then do its work. Okay? So I know that was a little bit complicated. I skipped a lot of the parts because those things are not as important as understanding the big picture view. Okay, so that was leucine. And, every time we talk about mTOR, everybody talks about leucine. And that's fine. Leucine very potently strongly activates mTOR. But it's not the only thing that activates mTOR, right? So sometimes I get a little frustrated because we're missing all the good bits too. Okay, what else are we missing? So we can activate mTOR through other amino acids. Okay, what other amino acids? Well, let's start with arginine, for example. That's a good one. We can actually activate mTOR with arginine. Now, I never hear people talk about that, and yet it's so important. So we have a sensor for arginine in the cytoplasm, and this is called CASTOR, CASTOR. CASTOR is going to sense the presence of arginine in the cytoplasm, and then it's going to act through GATOR2 as well. And the end result is the same. It's going to have Rag A/B and Rag C/D turn on, and then they bring mTOR to the lysosomal membrane. So we can actually activate mTOR that way. Well, we could also activate mTOR through methionine. Okay, so we have a sensor called SAMTOR. That's a methionine sensor in the cytoplasm, and SAMTOR will act through GATA2 and then bring mTOR to the lysosomal membrane. So you can see it's not just leucine. And in fact, the more amino acids you have, the more you can activate mTOR. So if you just have leucine alone, you activate mTOR for sure, but you only activate it by, let's say, I don't know, 20%. You add another amino acid and you get a little bit more activation. And by the time you add a third amino acid, you have it almost fully activated. Okay? So it's not just the presence of leucine alone that's important, it's other amino acids as well. Okay, so in fact, there are at least 10 amino acids that can activate mTORC1. Okay, so in alphabetical order, these are alanine, arginine, asparagine, glutamine, histidine, leucine, methionine, serine, threonine, and valine. Okay, so all of these can actually activate mTORC1. There's just a difference in the time course. So for example, leucine, arginine, and methionine, they activate mTORC within 15 minutes. And something like glutamine takes a lot longer. It takes about an hour for glutamine to turn on mTORC1. Okay, but basically all these amino acids actually can activate mTORC. So I know we talk a lot about leucine, but I just told you about massTOR, which senses arginine in the cytoplasm, and also mTOR, which also senses methionine. SAM actually stands for S-adenosylmethionine. It's just a modified methionine, right? But it's able to be detected by mTOR, and then we act to bring mTOR to the lysosomal membrane. All these things can activate mTOR. So that was one part. Okay, but there's a different part that we're going to talk about now. Because we also have an arginine sensor inside the lysosome. Okay, and this arginine sensor is actually the transmembrane part of SLC38A9, which is that carrier protein, solid carrier protein that I told you about, that is attached to the regulator. Okay, so that protein has a bit that's sticking into the lysosome, and there it detects arginine in the lysosome. Remember massTOR, that's detecting arginine out there in the cytoplasm, but we have a detector for arginine in the lysosome. And I'm just going to finish this part and then we'll step back a little bit, okay? So what happens? Why do we detect arginine? Why do we have to do that? All right, so we detect arginine in the lysosome, and SLC38A9 also does something else. Once it detects that arginine in the lysosome, it's going to also be an effluxer of amino acids inside the lysosome. And just means that it's going to be able to release amino acids that are in the lysosome out into the cytoplasm. Okay, this is kind of strange, right? Now, when I was learning about mTOR, I thought, oh, okay, this is interesting, and I thought the names were very cute and so forth. But there was one thing that stuck in my mind. Every time I read about mTOR, I'm like, the lysosome? The lysosome. So mTOR goes to the lysosome. And you know how you have like your really good friend and you think the world of her. And then one day you find out she's dating someone and you're like, really? Because you know that person and you're like, she's dating Aloysius. Aloysius is kind of a no personality kind of guy. He's kind of boring. He doesn't do much. No pep. Why are you going out with Aloysius? You could do better, girl, right? And that's kind of my thought when I heard about the lysosome. I'm like, really? mTOR? That famous mTOR? You're working at the lysosome? Not the mitochondrial membrane, not the nuclear membrane, the lysosome? Why? Right? And that stuck in my head. And it turns out, I think it bothered the researchers too, who were looking at mTOR. But then, in retrospect, it turns out that, it has a very specific reason to be at that lysosomal membrane. So let's back up a little bit and go back to the lysosome. I told you it's that recycling junkyard, right? Where, we bring all the cars to be scrapped, all the organelles, the defective mitochondria, for instance. You dump them in the lysosome, and the lysosome is acidified and has, these digestive enzymes that will break up these proteins into its little parts. Okay, now the lysosome is also kind of, I suppose, connected to autophagy, because when you are recycling parts, you first make an autophagosome, right? So you encircle the parts that are defective. You just want to isolate those parts first, okay? And you form what's called an autophagosome, and then you take this autophagosome and you kind of fuse it with the lysosome. And I told you the lysosome has this acidic environment and all these digestive enzymes, and then you break up the protein, and you have all the parts. Okay, well, guess what? Well, if you have all the breakdown products of these proteins, we can reuse them. So it makes sense for mTOR to be at that lysosomal surface, right? And it makes sense for mTOR to have the ability to sense that we have nutrients inside the lysosome, okay? And once we sense arginine, then we realize we got plenty of amino acids, and we can efflux through SLC38A9 the amino acids that are in the lysosome, right, out into the cytoplasm. And now those amino acids are available for mTOR to use in the process of making proteins. That's brilliant, right? So yeah, now we understand why we are actually at the lysosomal surface. Now, mTOR, when it's activated, also is going to inhibit autophagy, right? Because we're building proteins. I don't want you breaking down any more bits. But I will use the broken down bits already, right? Those that are already disassembled, and we can use those parts now to make more protein, okay? And then the big question is, why arginine? And we think this is because, ribosomes make up about 50% of the proteins in a cell, and ribosomes are very rich in arginine and also leucine. And we can actually have the breakdown of ribosomes. Maybe the ribosome is old, is defective. We can break those down in a process called ribophagy. Okay, and when we have ribophagy, then we're able to access a lot of this arginine, and this arginine therefore makes a good sensor and tells mTOR that we got plenty of amino acids in that lysosome that can now be effluxed into the cytoplasm to be used. Okay, so that's something I want you to keep in mind. It's not just leucine. I know we hear a lot about leucine, but there are tons of other amino acids that can turn on mTOR. And we also have a sensor, an arginine sensor, inside the lysosome to release the amino acids that have been broken down through autophagy into the cytoplasm, and we can reuse those. Other nutrients can also turn on mTOR. We know now that glucose actually also turns on mTOR. Nobody's quite sure of the mechanism, but people are pretty certain that glucose can turn on mTOR as well. All right, and just back to the lysosomes, we actually think now that the lysosome may be a storage organelle for amino acids and also nucleosides. Okay, so normally we know we can't store protein in our body, so whatever you can't use, you kind of get rid of, you pee out. But it turns out now that maybe, we can kind of store some of these amino acids in our body, and we do it in the lysosomes, okay? And besides that, we also store some of these nucleosides that are from breaking down these organelles. We can have a supply of those nucleosides inside and bases and so forth inside the lysosome that we can now reuse. So while we don't really technically have an organ to store our amino acids, you can kind of now think of the lysosome as a storage organ for those amino acids. Okay, so I thought that was pretty interesting and something that I wanted to bring to your attention. All right, so we talked about mTOR1, so let's talk about mTOR2 a little bit. It's less well known than mTOR1. mTOR1, as I told you, is important for growth and proliferation and making protein to do that, right? mTOR2 is also for cell proliferation and survival, but it's also involved in organizing the actin cytoskeleton in response to growth factors. So remember, in the previous episode, I mentioned this sort of scaffolding that we have inside the cell that's made up of the actin protein. It's called the actin cytoskeleton, and mTOR2 is very much involved in the laying down and organization of this actin cytoskeleton, because if a cell's going to grow, then that cytoskeleton is going to grow as well and shift, right? It forms the shape of the cell, for example. So mTOR2 is very much related to that, and it's really kind of stimulated by growth factors. And in the absence of growth factors, you really don't have mTOR2 activation. Okay, now I briefly want to talk about mTOR complexes in relation to diabetes, because while the mTORs are useful for cell proliferation, cell growth, right, they can also cause some problems. And we know that actually when we have overactivation of mTOR, then we can actually get diabetes. And, traditionally people have talked about mTORC1 signaling, okay? It phosphorylates the IRS, insulin receptor substrate, in the insulin signaling pathway, right? And as a result, it's going to inhibit that pathway and we become insulin resistant. And that's traditionally how people think of the mTORC1 having a role in diabetes. It turns out mTORC2 also has a role, and mTORC2 actually upregulates the degradation of IRS, right? And as a result, then you don't have IRS, and you also interfere with that insulin signaling pathway, and you can therefore have diabetes in the long term as a result. Okay, so I just wanted to mention that. And you can imagine, because mTOR is so important, it's going to have different effects in different tissues. So very quickly, I just want to look at mTORC1, for example, in fat tissue, where it seems to have a role in whole body metabolism. And when they've looked at mice that were knockouts for mTOR1, these mice were lean and resistant to diet-induced obesity, and it was felt that, okay, if we knock out mTOR1, then they're not going to, in the fat cell, right, have increase in size of those fat cells, and therefore they become leaner and so forth. Turns out mTOR2 also has a role in adipose tissue, but this time, if you knock out mTOR2, those mice become fat, right? So you get the opposite effect. And the reason is that mTOR2 in the fat tissue actually has an inhibitory effect on the pancreas and the liver, so that we're not producing a lot of insulin, and also we're not doing a lot of gluconeogenesis. But if you knock out then mTOR2, then you lose that inhibition, and now we make a lot of insulin, and we also have increased gluconeogenesis, which then leads to insulin resistance, okay? So you can see that in different tissue, you can have different effects. In muscles, of course, famously, it helps the muscles grow. And also, I didn't mention this, but when we talk about growth, we're not talking about making new cells here. With mTOR, we're actually just talking about increasing the size of the cell. Okay, so in terms of muscle, you're just laying down more myofibrillar protein, and as a result, that muscle cell is going to grow in size. So you're increasing biomass. You're not actually making new cells there. Okay, I just wanted to clarify that in terms of growth. Okay, and then there's some bits here that I'm going to skip. We'll probably do another time. But there's one other thing that I think will be of interest to you. Here we go. And I'm going to bring it to your attention. This is from Castellano et al. I don't have the year here, but you can look that up. And this is very, very interesting because we talked about how amino acids can turn on mTOR. We talked about, not just leucine, but a whole set of amino acids and growth factors, right? And energy levels through AMPK, so we can detect, whether we have low ATP or high ATP, and that can also turn on mTOR. And glucose also is another signal to turn on mTOR, right? Well, it turns out that cholesterol itself is another signal. Okay, so this paper, they use human embryonic kidney cells, and when they deprive those cells of cholesterol, they suppress mTOR1 signaling. Okay, but when they gave exogenous cholesterol or LDLs, and remember, LDLs are the lipoproteins that are carrying primarily cholesterol, then we activate mTOR signaling, okay? And this does not involve the PI3K-AKT signaling pathway. Independently activates mTOR. And this is specific for cholesterol because when they did the experiment with other oxysterols, with steroid-related compounds, with oleic acid, which is found on the LDL, right? There was no activation of mTOR1, okay? So it turns out that not only do amino acids and glucose, act to turn on mTOR, we can turn on mTOR with cholesterol. Does this not make sense? And there again is the beauty of the lysosome, because if you remember from the glycocalyx episode, I talked about the LDL receptor taking in LDL, right? Bringing it into lysosomes, right? Where we can break down the LDLs and then we recycle that LDL receptor. So that magic word is lysosomes. Now we have these lysosomes that are enriched with cholesterol, with LDL carrying the cholesterol, and we can actually turn on mTOR. Why? Because if we're going to grow, we're going to need cholesterol. Cholesterol is very important. You're going to make more organelles. Well, you're going to need the cholesterol for the membranes. You're going to increase the size of the cell. You need more plasma membrane. You're going to need that cholesterol. Vital, absolutely vital. So independent of glucose and amino acids and growth factors, cholesterol itself can turn on mTORC1, all right? And I thought you would like this part as well. This is from the paper I'm going to quote. Inhibiting endogenous cholesterol synthesis with mevestatin also suppressed mTORC1 signaling, which fully recovered following washout of the drug for 1 hour. Okay, I find this pretty interesting. So now if we use a statin, right, and statins actually basically decrease cholesterol levels, the synthesis of cholesterol in your body. So we use the mevestatin and we decrease cholesterol levels. And what do? We decrease mTORC1 signaling. Now, traditionally, when we've talked about statins, right, and muscle atrophy in relation to statins, you hear people talk about upregulation of myostatin, which is a protein that inhibits, muscle growth and muscle synthesis, right? Okay, but this is a separate pathway because now if you use the statin and you are inhibiting mTORC1 activity, then you also in the muscle don't get any muscle synthesis. So pretty interesting, right? The other thing that we can maybe throw in here is there's a sterol transporter called Niemann-Pick C-type 1, right? And PC1. And that's very important in taking cholesterol out of the lysosome into the cytoplasm where it can be used. Okay, so it's a transporter. And what we know also is that when you have NPC1 bind to mTOR, then basically you inhibit mTOR. Okay, so we have the mTOR, we have the lysosome sensing the cholesterol, and we believe this is through SLC38A9 as well. So pretty important carrier there, right? SLC38A9. So we can sense the presence of cholesterol and we now activate mTOR and we start protein synthesis. Okay, and this NPC1 carrier takes that cholesterol and brings it out into the cytoplasm. But when there's no more cholesterol left to take out, well, it's hanging around and it says, oh, well, I might as well hang out with mTOR. So it goes and binds to mTOR, and then that's a signal to mTOR, hey, there's no more cholesterol left. And so we inhibit mTOR, we turn it off. So that's kind of nice, right? We know that there are these diseases where people lack NPC1, right? And they have, therefore, as a result, accumulation of fats and lipids and cholesterol in the lysosome. And this kind of gunks up the cell and causes dysfunction and a lot of neurodegeneration. It's a genetic disease. And interestingly, they found that if they actually could inhibit mTOR signaling, they could stop or decrease the mitochondrial dysfunction. And these people symptomatically, at least for a little while, get better. They still have the gunk, they still have plenty of cholesterol stuck in the lysosomes, but they don't have the mitochondrial dysfunction associated with it because now we have shut off mTOR. Okay, so I find that really interesting. And like I said, these things are all connected. I skipped a lot of things, but it's getting late and I got to wrap this up. So that's what we're going to do very quickly. We just had a brief introduction to mTOR, and I talked about it being the target of rapamycin and how we have different mTORs in us, we have the complex 1 and complex 2. And then I basically went through the bodybuilding model, right? And then I built off of that. We talked about how we sense the nutrient and then we activate the complex such that we bring mTOR to the lysosome. And then under the influence of growth factors like insulin, we also activate the other arm, which is basically bringing Reg to the lysosomal surface as well. And when Reg is there, it can directly activate mTOR and we initiate protein synthesis. Okay? And then we talked about how leucine is not the only amino acid. I named 10 others. And the most important ones would be leucine, arginine, and also methionine. And they activate mTOR very strongly. But arginine in the lysosome as well will activate mTOR, because when we sense the arginine in the lysosome, then we know we have plenty of amino acids present. And SLC38A9 will also efflux those amino acids in the lysosome into the cytoplasm for mTOR to use. Very convenient. Glucose too can activate mTOR, but now we also know that cholesterol can do that. So when we take in LDL into the lysosome and we access cholesterol there, we can sense the cholesterol there and we can switch on mTOR independently of the amino acids and the other pathways, okay, just purely by the presence of cholesterol alone. And we have a transport carrier. This is the NPC type 1 carrier protein that transports the cholesterol out to the cytoplasm. However, when we run out of cholesterol, then NPC1 goes and associates with mTOR and inhibits it. And that's when we stop the action of mTOR, which I think is a beautiful system. But we also learned something very important, and that the lysosome isn't just this boring recycling waste center. It's also where we possibly are storing amino acids and, storing and recycling cholesterol as well, and also nucleotides for synthesis of the cell. Okay, and in fact, I could probably do a whole episode on lysosomes because it's a very, very interesting organelle. Much more interesting than I thought. So sorry, Aloysius, you're a pretty interesting guy after all, right? Okay, so that's it for this episode. I know I missed a lot of stuff. There's plenty of other stuff that I didn't get to talk to you about, but we'll probably get to it in other episodes. I hope you found this interesting, but at the very least, I just wanted people to understand that mTOR is way more than just leucine. Okay, so signing out now from VLMD Rounds, I am Dr. Vivian Lowe, and I sing the body electric. Bye.